here, or they move from here to here, or that moves in and that moves out. No, that's not happening. I'm doing that on paper, or in this case on the board, as a way to generate a picture of what cyanate looks like. Cyanate does not alternate between these structures. None of those are real. So cyanate doesn't look like this on Monday, that on Tuesday, that on Wednesday, that on Thursday. Cyanate is always this thing, or a close approximation. So our action of moving electrons, that doesn't happen. Right? I use the individual structures to help me get a picture of the species. I use James Bond and Indiana Jones, which are not real, as a way to conjure an image of the true boyfriend. But if you knock on the boyfriend's door on Monday, James Bond doesn't answer the door. And if you knock on the door on Tuesday, Indiana Jones doesn't answer the door. The boyfriend answers the door both days. The boyfriend is the boyfriend. Indiana Jones and James Bond don't exist. And the boyfriend doesn't oscillate between the two. So this business, these things are just a way for me to get an image of true cyanate. And I will tell you, if you take cyanate and do an X-ray of the cyanate ion, this bond is not a triple bond. And you could tell, because triple bonds are short, there's a certain length of triple bonds. Double bonds are a little longer. If you measure the length of this bond, it is somewhere between triple and double. If you measure the length of the NO bond, it's not a single bond, it's not a double bond, it's somewhere in between. Closer to this than that. I can do what's called an electron density map. So I can measure the charges on the individual atoms in any structure. If I do an electron density map of cyanate, the charge of this carbon is not -1.5, it's not -1, it's not -2. It is somewhere in the middle. Closer to this than that. If I measure the charge in the N, it is 1+, dead on. If I measure the charge in the O, it is neither -1 nor is it 0. It's somewhere in between, closer to this. So the image I conjure for cyanate actually is pretty real. It is borne out by the evidence, by the lengths of the bonds, which are intermediate between the two extremes, in this case structures 3 and 4. It is borne out by the electron density maps, right, where the charges are intermediate between the two structures. Okay, so let's stop there on resonance. We talk about resonance condition and moving electrons around and so on. We're going to change focus and talk about bond energies and Morse curves. And we won't quite have time to do the next part, which is fine. We pick it up in the next lecture. So let's talk about bond energies and what we mean by bond energies. So the bond energy, and you have met this as well to some extent in Gen Chem 2. The bond energy we're going to call is the energy required to break a bond, and it's the energy released when a bond is formed. So we're going to define the bond energy in two ways. It is the energy I need to invest in breaking the bond. It is also the energy that is released when the bond is formed. So we're going to digress for a little bit with that bit and talk about what's called a Morse curve. And what we're going to do is we're going to imagine for a moment the formation of a simple bond. Let's say the HH bond in dihydrogen, in H2. And let's for a minute talk about how that bond is formed. So let's imagine we have two hydrogen atoms that are coming together to form the H2 bond. So I'm going to put a plus here for the hydrogen nucleus and a dot for the hydrogen electron. So I want to draw a plot of the energy, and I can use H for the enthalpy, against R, which is the internuclear separation, right? The internuclear separation. So let's start off where these atoms are infinitely far apart. Now, for an atom, particularly one as small as hydrogen, infinitely far apart could be a millimeter, right? So at the beginning, when they're very far apart, the nucleus of this hydrogen does not feel the electron on this hydrogen. Nor does this nucleus feel that electron. They're completely unaware of the other's existence. There is no force of attraction between them. There's no interaction. But the pair of atoms have a certain collective energy, which is a non-zero value. So let's say as R tends to infinity, their enthalpy value is here. That's where we're going to start. What we're going to do is slowly move them towards each other. And for a while, nothing is going to happen. We're going to move them towards each other. They're not going to feel each other, and there's no change in the energy of the system. But you get to a point where the atoms move close enough that the nucleus of the one feels the electron of the other, and a force of attraction takes place. The nucleus of the other feels the electron of the other, and the force of attraction takes place. Attraction lowers the energy content, and the system's energy starts to fall. Now, at some point, you get to an optimal separation, right, where you end up with an ideal distance between the nuclei and the electrons, and that we're going to call R naught. R naught is my bond length, right? So R naught, which is my optimal separation, is what I call the bond length. So when you look at text and it says the length of a something bond is 10 angstroms, that's what they mean. The bottom of the curve, the value of R there is 10 angstroms. If I try to smush this below R naught, the special one, the nucleus of this starts to feel the nucleus of that, right? And at that point, nuclear-nuclear repulsion takes place, and the energy content suddenly spikes. So here, attraction equals repulsion equals 0, because they're not feeling each other. And you know, this is like phase 1 of the plot. In phase 2 of the plot, attraction is greater than repulsion, which is why they're moving together. In phase 4 of the plot, repulsion is greater than attraction, which is why the energy content goes up. Now, at this point, which we call point 3, attraction is still greater than repulsion, which is why the bond stays together. If attraction is equal to repulsion, there's no reason, there's nothing to keep it together. Something has to hold the bond together. So at this point, attraction is still greater than repulsion, right? But you're at that critical point, right? Which is just enough to hold, for nuclear electron attraction to be just greater than nuclear-nuclear repulsion for the bond to hold, okay? Now, if I look at this graph, there are two values from it that the chemist is interested in. One value, and I'll just take these off for a second. One value, as I already mentioned, is the value of R, the internuclear separation, at minimal energy. The value of R at minimal energy, at minimal energy, is called a bond length. But the other value of interest is this one, which is essentially the energy gap, the delta H, between the bonded atoms and the free atoms when they're not feeding each other. The energy released when the free atoms bond, we're going to call that the bond energy. It is also the energy required to take the bonded system and break the bond. Right? Because when the atoms are bonded, to take them from here to here means the bond is cleaved. That is also the same value. So the bond energy, that's what this is. This is the bond energy. And a lot of people write this as, instead of a delta H, write it as a DH. Right? That is the bond energy, which I can define in two ways, depending upon the direction in which it's happening. It's either the energy required to break the bond, to go from here to here, or the energy released when the bond is formed. So there are two values that we take from the curve, from the Morse curve. The bond energy and the bond length. Let's say, for example, I'm looking at a couple of different scenarios. So let's say I want to explore CF, the CCl, the CBr bonds. So CF, CCl, and CBr bonds. And I say, on the same pair of axes, sketch the Morse curves for those three. On the same pair of axes, sketch the Morse curves for the CF, CCl, CBr bonds. What is the question asking you? It's asking you to sketch the curve and to highlight relatively what are the R naughts, the bond lengths for CF, CL, CBr. What are the bond strengths for the CF, CL, CBr? How do I know that? Here is carbon, here is fluorine. So the CF bond is going to have a certain length. That's my R. So carbon and fluorine. Right? Chlorine is a bigger atom. That's carbon in all the cases. Chlorine is a bigger atom. So the CCl bond is longer, CL, is longer than the CF bond. Bromine is an even bigger atom. So the CBr bond is longer than the CCl bond. Right? Small atoms form short bonds. Short bonds are strong bonds. We talked about that in day one. Because in a short bond, you are placing the electron pairs as being shared close to the nuclei. And the force of attraction depends inversely on the distance between the charged particles. When the atoms are smaller, the bond is shorter, the electron pair that's being shared and the nuclei are closer together. R is small, F is big, force of attraction. So this F here is force, not fluorine. So what this means is, if I ask you to sketch a curve, sketch the same pair of axes, the plots for CF, CCl, CBr, I am asking you to tell me how does the bond length change, how does the bond strength change. And that is entirely dependent on where the atoms are on the periodic table. These are group partners. As I go down the group, the atoms get bigger. As the atoms get bigger, they form longer bonds. So R goes up. As the bonds get longer, they get shorter because the nuclear electron distance rises. So the force of attraction drops. So in the same pair of axes, what would this look like? I'm going to just take this off for a second. Now, I'm going to make something a little bit simple here. This is R. And I'm going to say that CF, I'm going to write CF in red. I'm going to write CBR, CCL in green, and I leave CBR as blue. So I'm just going to draw for now the C, since I have green out already, I draw the CCL curve. So I'm going to draw this. Start with CCL curve. I'm going to draw this, and that's my curve. That's for CCL. That's my reference. Where is CF? Well, the CCL bond has an R0 value, the CCL. Fluorine, as a smaller atom, will form a shorter bond. So we're going to be here, we're going to slide towards a lower value of R. So let's pick it. Let's say this is the value of R. So that's R0 for CF. Okay, good. What else is different? Well, the bond division being shorter is stronger, which means this gap is deeper. So, and here's the approximation we're going to make. In reality, and if you guys are chemistry majors and you do physical chemistry, it turns out that the curves are going to slide up and down. We're not going to worry about that for this. This is a very qualitative approach. But if I start here, CCL, I'm going to end up going deeper, right, for CF. And what does that mean? My bond is shorter, my bond is stronger, right? More energy required to get out of the hole, to the free atoms, more energy released when the bond is formed. What does it look like for CBR? Well, the CBR bond is longer. The CBR bond is longer. So we're going to slide the Morse curve to the right, to a larger value of R. It's also weaker. So it wouldn't be as deep as any of these. So if I start here, I'll do that for CBR. So my R0 value for CBR is greater, and the DH, the bond, well, that doesn't look very convincing. So let's do this, so it's more convincing. So the bond strength, the energy released or required to break it, released when it's formed, or required to break it, this is less than that, So if you ever asked, and let me suggest that you might very well be, to sketch the curves, that's what we're looking for. I would not mess, if I were you, with sliding these along the axis. Because if you slide them, and you slide them in the wrong direction, that's not going to be right. So let's just approximate for now that they're all starting at the same level. They're not, but let's approximate that for now. Okay, so those are my Morse curves. And again, this reinforces the idea that to break a bond requires the input of energy. To go from bonded species to free atoms requires the input, and when bonds form, there's a release of energy. It also supports the idea that bonding stabilizes, right? When I'm not bonded, here's my energy. When I'm bonded, my energy content goes down. So bonding stabilizes, which is why, for example, when we were drawing the Lewis structures, one of the parameters we use to gauge relative stability is how many bonds you have. If bonding stabilizes, surely the more bonds you have, the more stable you are. And folks, that actually makes a lot of sense. I think we talked about that when we were looking at the properties of carbon. If I'm living in Fort Smith, and the only thing that keeps me in Fort Smith, let's say I'm in Fort Smith and I have a decent salary. So that is one thing that bonds me to Fort Smith. But suppose my wife has family in Fort Smith. Well, that's two things that bond me to Fort Smith. So I'm going to be more rooted here, more stable here. I'm less likely to leave because I've got two bonds here. What if I love the weather in Fort Smith? Well, that's three things that will keep me in Fort Smith. What if I like the hikes and the lakes and the rivers? Well, that's four things that keep me in Fort Smith. The more bonds I have, the more stable I am. If I like the salary, my family is here, I like the weather and the climate, and I like the vistas, maybe the food, or whatever. The more bonds I have, the less likely I am to move. The more stable I am where I am. Okay. Let's talk a bit then about again about bond energies. So now that we know what a bond energy is and where it comes from, let's talk a little bit about what we do with them. And I will just introduce this, and then the rest of it we'll start in the next lecture. Suppose I look at the reaction between methane, CH4, and oxygen, O2, and they react to form carbon dioxide and water. Now we know that reaction releases energy, so it is exothermic. But I want to figure out exactly how much energy that releases. Right? How much water can I boil? Right? How much energy is released to boil water or whatever. What I need to do is to figure out how much energy I'm putting in to break bonds, because bond breakage, you just saw from the Morse curve, bond breakage requires the input of energy. And the essence of chemistry, particularly organic chemistry, is the breakage of bonds and the formation of bonds. And clearly, at the beginning, the carbon is bonded to 4 H's, the O is bonded to itself, and in the end, the partners have changed. So the essence of this reaction is I broke all 4 of the CH bonds. I broke the OO bond. And I formed in their stead CO double bond and 4 OH bonds. So how do I get the energy change in this reaction, the delta H of reaction? I'm just going to do an inventory. How much energy did I consume to break these bonds? How much energy did I get out when these bonds were formed? That is very nicely described by what's called, and we've met this in Gen Chem 1 and 2, a reaction profile diagram. And a reaction profile diagram is a plot of H enthalpy against what we call the reaction coordinate. And the reaction coordinate is a funny term which incorporates both time, so this is time 0, and this is the reaction progressing in time, but it also incorporates the extent of bond breakage, how far these have progressed, and the extent of bond formation, how far these have progressed. So I'll pick a very simple example and then we'll stop. Suppose we have a simpler example where I'm reacting A2 and B2 to make 2 ABs. And I'm going to pick a really nice simple case and say, look, we're going to start off here with some energy that A2 and B2 collectively have. For the moment, let's say the reaction is exothermic. So I'm going to have here 2 ABs. So what is happening is, I'm going to have to put in energy to break the AA and the BB bonds. And I can imagine in a very simple-minded way that at the top of the hill, I basically have free A's and free B's. I have succeeded in cleaving the AA bond and the BB bond. At the top of the hill, my 4 species have 2 options. They could recombine and fall back down where they came from, And they fall because as the bonds are being made, the energy decreases. Or they can combine in a different way. A to B, A to B. And again, because I'm making a bond, the energy content will decrease. So the ascending portion of the plot represents the energy I put in to break the AA bond and the BB bond. That is the energy consumed in bond breakage. The descending portion of the plot represents the energy released when the AB and AB bonds form. Now obviously, if I release more energy than I put in, overall my delta H is going to be negative. If I consume more than I get out, then the delta H is positive. And that's an endotherm. If the amount I consume and the amount I release are the same, then that's a thermoneutral reaction. Okay? And I will remind you, just very quickly, what delta means. Delta anything is a change. So delta of anything is the change. But it is the final state minus the initial state. So delta H is the H of the product minus the H of the reactant. So in this scenario, if I look at the energy value, this is the energy of the product. This is the energy of the reactant. In this reaction, the energy of the product is smaller than the energy of the reactant. This number is smaller than that. If I have 2 minus 5, I'll get a negative number. So in a case like this, where the energy of the product is less than that of the energy of the reactant, when I have released more than I gain, in this scenario, delta H, right? Delta H is negative. So see, delta H is less than 0. In other words, it's negative. And this is an exotherm. Because the system has overall lost this much energy. So heat energy has gone to the outside. Now what do I mean by the fact that it's lost energy? When the molecules are reacting and they're releasing heat, where does it go? It goes to the solvent, which goes to the glass, and when I touch it, it feels warm. So exotherms release heat and the system gets hot. In this scenario, what happens? Well, the energy of my product is now greater than the energy of my reactant. So when I get delta H, which is HP minus HR, well, this number is bigger than that one. So that's a positive number. 5 minus 2 is positive. So in a case like this, delta H is greater than 0, or it's positive, that is called an endotherm. Right? The system gains that much heat, right? The heat goes into the system as I convert from reagent into product. Okay, so we'll stop there and pick up from here in the next lecture. Thanks.